Recall that water pressure increases with depth, and that a consequence of this on objects in water is buoyancy. Recall that a submerged object is buoyed upward because there's more water pressure at its bottom than at its top. Water pressure exerted against the top of this submerged block, multiplied by the block's top surface area, produces a force shown by the downward red vector. For emphasis, its pressure multiplied by its top surface area produces this downward force. The bottom of the block is deeper, so there's more water pressure exerted against the bottom, and multiplied by the bottom surface area produces this upward force. So we have two forces, down against the top and up against the bottom. The difference in these forces produces what we call the buoyant force. Now what if the block is vertical? Then there's a greater difference in depths and a greater difference in pressures between the top and bottom, and correspondingly greater difference in downward and upward force vectors. So does this greater difference in forces mean there's greater buoyant force in this vertical position? It turns out no. Greater pressure difference multiplied by the correspondingly smaller top or bottom surface area produces a buoyant force, which is exactly equal to the smaller pressure difference on the block in its horizontal position multiplied by its larger top or bottom surface area. So the buoyant force is the same either way. Get it? Archimedes' principle bypasses this by telling us that the buoyant force equals the weight of water displaced regardless of position. And clearly the block displaces the same amount of water whatever its position beneath the surface. In addition to buoyant force on the block, there's its weight. If the weight of the block is less than the buoyant force, the block would rise. If the weight is more than the buoyant force, it sinks. If the buoyant force and weight are equal in size, then neither rising nor sinking occurs. A good way to determine whether rising, sinking, or neither occurs involves density. Recall that density is the ratio of mass to volume. Rho equals mass per volume. Or if expressed as weight per volume, then we're talking about weight density. Here's three important rules. In object 1, more dense than water sinks. 2, less dense than water floats. 3, with equal density as water, neither sinks nor floats. So an iron nail sinks, a piece of wood floats, and a fish with a density that matches water neither sinks nor floats. This makes sense. These rules apply to fluids in general, even air, as we'll see in later lessons. Let's look at changes in density. In the previous screencast, we saw how our submarine changes its density by changing its weight. With ballast tanks filled with water, its weight, and consequently its density, increases. And once submerged, it becomes lighter by blowing water out of the ballast tanks, becomes less dense, and rises. It can adjust its density. A fish can similarly change its density. Here's a fish that wishes to reduce its density and buoy to the surface. What's it do? It expands its air sac and increases its volume a bit. Up it goes. If it tightens and reduces the volume of its air sac, too small to see here, its density increases and it sinks deeper in the water without effort. You can do the same thing in your bathtub. Take a deep breath and hold it, and you'll note that you rise a bit in the tub. Then exhale and you feel your back bumping against the tub bottom. Let this be your physics assignment the next time you're in a bathtub. In the previous lesson, I posed the problem of the weighted balloon. I asked what would happen to a weighted balloon, barely floating, if it were pushed beneath the surface, and then let go. Would it float back to the surface, stay where it is, or sink? And recall, I gave a hint in thinking about squeezed air. What's your answer? Well, let's make the hypothesis that the balloon sinks. If it were to sink, what would this say about any change in density? To sink, it means it would become denser. But how? One of the terms in the equation for density, weight over volume, has to change. First, weight. Would the balloon be heavier when beneath the surface? I think you can agree no. Note density involves volume. For an increase in density, would this mean an increase or a decrease in volume? That's right. The volume would have to decrease. And why would the volume of the balloon decrease when deeper in the water? Did you say because water pressure increases with depth? Is that what you're thinking? That the greater water pressure against the balloon squeezes it smaller? Does that make sense? And yes, it does. So the balloon's density increases when pushed beneath the surface, which means it sinks. Again, ask your friends this question and it gets interesting. Yum physics. Now I want to leave you with a question. As the weighted balloon descends deeper and deeper, does the buoyant force on it increase, decrease, or remain the same? Defend your answer. Until next time, good energy.